All right, so now to again some more key features. And so we want to find vertical asymptotes and holes. So how do we determine, rather, so we just looked at some vertical asymptotes and essentially we asked what happens around them, right? So from the left of 3 I go up forever, from the right of 3 I go down forever, so on and so forth. But the question is, how from algebra can I determine vertical asymptotes and these thing called holes, which we've seen before in a prior section, but we didn't discuss as a whole directly. And so you'll see that once we review some other things. Anyways, let's dive in. So a hole, or what we call a point of discontinuity, is the following. Any algebra that, catch this wording, caused 0 in the denominator, but was able to be factored and canceled. And vertical asymptotes, catch this wording, is any, I'm going to abbreviate this to algebra, that is left over after factoring which can still cause 0 in the denominator. All right, interesting. So evidently, here's the key thing. We're going to be factoring, and we're going to be careful to note which things we're able to cancel and which things are left over that are still in my denominator. So let's see what we're talking about here on these first two examples. In these first examples, the question is, are these two things factored? And the answer is yes. And by two things, I mean numerator and denominator. Is your top completely factored? Yes, it's a plain simple x. There's nothing I can do with it. On the bottom, is this factored? Yes, it's an x plus 7, and 1 and 7 and x and no x's don't share anything. So both your numerator and denominator are completely factored, so to speak. Now then the question is, can any of these cancel? And careful, don't say, oh, x's can just cancel and I'm done. Because those, rather, this x plus 7 is adding, and you can only cancel over the fraction bar if things are canceling by multiplying. All right. Now, again, early on, or rather, I think it's important to review this concept. And once again, I'm going to pull out just a blank page, not on the notes, and just show you something here. So let's say, we had 15 over 25. And the question is, can this be reduced, is another way of saying it. The answer is yes. Now, why can it be reduced? Because 15 is 3 times 5, and 25 is 5 times 5. And the common 5's cancel, and they cancel because they were multiplying, and I'm left with 3/5. Now, watch what happens instead. What if I do something crazy like this? What if I say that 25 is 5 plus 5 plus 5? Or sorry, 15 is 5 plus 5 plus 5. Or you know what? Here, let's even do it this way. I want to make it look similar. Let's say that 15 was 10 plus 5, and 25 was 20 plus 5. And let me just cancel these. Look what I get now. I get 10 over 20, which is 1/2. And so one of these is clearly incorrect because I can't get two completely separate answers for the same reduction of a fraction. And the one that's incorrect is this one. This is totally wrong. And so the point I'm trying to make here is canceling over a big division symbol when you only see pluses and minuses in between is a big no-no. Can't do it. Absolutely not. You can only cancel over the fraction bar when both the numerator and denominator have that thing multiplying to the entire expression. So that is a very long way of saying these x's are not going to cancel because this doesn't say x times 7, is maybe what I'm saying. Okay, so what does that mean then? Well, it means this. There are no holes in this graph because all my algebra was factored, but nothing canceled. Okay, now that I've taken that into account, is there any algebra that can still cause 0 in my denominator? You betcha, it's x plus 7. And so that means my vertical asymptote is x equals -7. Now, if you're sitting there going, wait a minute, Mr. Rao, that feels eerily familiar to what I did at the very beginning when I was finding the domain, great. Then you just figured out the big concept here. Your vertical asymptotes, these vertical slashes are what introduces the union symbol when we write out our domain. And it's really, to say it again, or to say it differently, the reason we need that union symbol is to show that your domain is cut into pieces, and literally you have these vertical cuts in your graph that is chopping what's allowed into pieces. Interesting. Okay, for the next one. Is everything factored? I would argue yes, because I can see in my denominator this x plus 1 is already had the x factored out, and this x plus 3 cannot be factored. And once again, the question is, does any of this cancel? And once again, the answer is no, because this says x plus 3. I don't see x plus 3 entirely anywhere on the bottom. I see x plus 1, but that's not an exact match. And I see a simple x, but there is just no one simple x. So there are, once again, no holes because we factored, but there were no matches on top and bottom. There was no 5 and 5, like I kind of just said, to cancel out. But then that means there are two vertical asymptotes this time. There's a vertical asymptote at 0, because I can plug 0 into this simple x and get 0. There's also a vertical asymptote at -1. Two vertical asymptotes, no holes. And if you're saying, that sounds crazy, Mr. Rao, I haven't seen something like that. Spoiler alert, yes you have. Two vertical asymptotes, no holes. So that's kind of how you would get a structure like that graph. Okay, moving on. We've got a few more to go through. So up next, oh man, I hate to give you a trick question, but I did it so that you wouldn't have to discover it on your homework. So take a look at this. Is your denominator factored? No, because I see an x squared plus 16. But then the question is, can I factor it? And are there factors of 16, careful, that add to nothing in the middle? And the answer is no. Then the question also is, can this x cancel here? And the answer is also no, because there's no common x to divide out of everything, so to speak. So nothing's shared on the numerator and denominator. Now that also means, finally, that there are no holes because nothing canceled after factoring, but there's also no vertical asymptote because, and we've seen this idea before, there was a square plus a number. There's no way of making that 0 for the reasons we discussed, I think, in our first video in this section. So, interesting. It's possible for these crazy rational functions to actually have no holes and no vertical asymptotes, but still definitely have a crazy funky shape. All right, well, let's continue and do number 4. Number 4, we're asking the same question, is everything factored? And the answer is potentially no, but this time the answer is definitely no, because my numerator is a difference of squares, as we've seen many times in this unit, or I guess section 3.5. So that's what I get when I factor my numerator. What multiplies to 81 and subtracts to 0 because there's no simple x? -9 and +9, or vice versa. Now, finally, here's something else that happens. Now that I've factored, are there any perfect matches that are multiplying in my numerator and denominator? And the answer is yes. There's an entire x minus 9 multiplying to anything else in the problem. That's why it's written in parentheses to show it's multiplying to everything else. And there's an x minus 9 all by itself, but technically multiplying to a 1 on the denominator. So we get our first cancellation, which means we get our first whole, which is at x equals 9. Now we look at the leftovers. The leftovers are x plus 9, technically over 1. Is there any way of making this 1 in the denominator equal to 0? And here's a big vocab lesson. No, because there are no variables in my denominator. So there's no way I can make my denominator vary or be anything other than 1. So because there are no variables, your denominator cannot vary. It cannot change. So there's no making this 1 into a 0. So there are no vertical asymptotes. Now I'm going to, once again, I'm going to pause myself for a second and show you the graph of this to show you what it looks like and show you where we've seen this concept before. All right, so I've graphed our crazy wild function, and what you should be thinking is, wait a minute, Mr. Rao, this function doesn't look crazy and wild like the rest of them. And you're right, and that's when you look back at what we were able to factor and cancel out and look at what we were left over with. This, although I wrote it over 1, you don't have to write it over 1. And this is just a regular mx plus b line. But here's the catch. The catch is at -9, the thing that canceled out. Oh, 1 minute. -9? Sorry, +9, because the whole was at +9. Here we go. Scared me for a second. There is the whole, as we call it, or the point of discontinuity. At 9, it says undefined. So what happened here? The answer is, well, we ended up with this. After we dealt with our algebra, we were left with x plus 9, a regular old line. Now, a regular old line can have anything plugged into it, but this wasn't a regular old line to begin with. It had something that could make 0 in the denominator. Now, even though that canceled, the shadow of, or what I started out as, is still in the problem somewhere. So I did reduce this to be a simple looking line, but I still had to state that essentially at one point this algebra was not allowed to have 9 plugged into it. And so we call that a removable discontinuity. It would otherwise look like a regular old whatever the graph should be after that's gone, but I still need to replace that with a open circle, so to speak. That's something we really won't explore in terms of showing those on the graph, but I just wanted to show you here what we're looking at. All right, let's continue and do the last example here. The last example is finally your full kind of factoring practice, and so we haven't done full factoring in a minute, so it's a good thing we're seeing it now. This is saying what multiplies to 24 and adds to 10, so try to think about that for a second. What can multiply to 24 and add to 10? And the answer is 4 and 6. Now the question is, how do you multiply to positive 24 and add or combine to negative 10 with 4 and 6? And the answer is they're both negative. So catch that kind of rephrasing of the question. It's first just what can multiply to 24 and add to 10? We just say 4 and 6. Then at the very end we say, okay, now that I know it's 4 and 6, how do 4 and 6 add or combine to be negative 10? And the answer is they're both negative. Also, hey, look, that's convenient, because now what do I have? I've got, it isn't written in parentheses, but I've got all that in the numerator, and I see it a perfect match in the denominator, so those cancel. But watch how it cancels. Now there's 1 over x minus 6 left over. So what does that mean is going on here in this question? It means there is a whole. The whole is at x equals 4, because that's the root of the canceled algebra. But now we finally bring back the full definition. So any algebra that caused 0 but was able to be factored and canceled. That was a whole, found that. Any algebra that's left over after factoring, which can still cause 0 in the denominator. I guess I should have said after factoring and canceling, but I think that was implied. The idea is now there's still something in my denominator that can still make 0. So finally, I have a graph that has a vertical asymptote and a hole at the same time. And let's just see what that graph looks like. All right, now this, as we're going to discuss in a few minutes, has the true kind of classic rational shape. And we can see that at 6, here's positive 6. There's my vertical asymptote. You can see it's not actually written on the graph anywhere. It's an invisible line that we draw the dashed lines in to denote. And at 4, where's 4? Here's 4. Oh, there it is. There's my point of discontinuity or the hole. So interesting. So all that's right there in this equation. Awesome. All right, we've got 4 minutes left, and because we're trying to keep each one of these to 20 minutes. So I want to get through this last quick section here. I think we can do it. So I want to look at horizontal asymptotes. Once again, end behavior is what we're talking about here. And so we've learned about end behavior, but now the idea is, to say it this way, rational functions have, I know they look simpler than this, but we could say that there's a polynomial on top and a polynomial on bottom. And we've already learned that for polynomials, the first and highest degree, I guess first if you've written them in order, the highest degree term is the thing controlling your end behavior. And so what this is saying here is assume that you have found your highest degree term in the numerator and your highest degree term in the denominator. And what can we learn about these that will tell us about horizontal asymptotes? And so there's 3 scenarios. Catch this. What if n is greater than m? Now, what does that mean? That means what if your highest degree exponent in the numerator is greater than your highest degree exponent in the denominator? Well, then guess what? There will be no horizontal asymptote. Now, there are such thing as slant asymptotes, but we're not going to worry about that. All right, moving more quickly, what if n is less than m? This is interesting. There is an HA, but it's the same answer every time. It's y equals 0. Just to say out loud, you've encountered that before. I've gone back to this graph so many times, but it's this graph right here. This graph, I don't know what the algebra is that made this graph. Cough, cough, I might. But what I do know is that this graph's top exponent was less than the graph's bottom exponent, or I guess the algebra's top exponent was less than the algebra's bottom exponent, because I can see a horizontal asymptote hugging towards 0 and hugging towards 0 from both sides. So that must have been that scenario. Now the last one, if it's not greater and it's not less, then they must be equal. And what happens then? You do get a horizontal asymptote, but the horizontal asymptote finally is a over b. I bet you were wondering, why did we write down the coefficients and never use them? Because they're right there in our third example. All right, well, with that being said, let's determine the horizontal asymptotes of these 3. And you should honestly be able to answer each one of these, hopefully in about a minute. Take some time if you want to try it, but we're going to go ahead and blaze forward. So, I see my numerator and denominator. The highest degree in the numerator is 1. The highest degree in the denominator is 2. So the numerator's degree is less than the denominator's degree. So which scenario are we in? We're right here. So the HA is y equals 0. The top was less than the bottom. All right, up next. Top is greater than the bottom. Hopefully, you know that then means there's no HA. And well, there's 3 scenarios and there's 3 examples, so you guessed it. But even so, the highest degree is 2, highest degree is 2. So because they're equal, my HA is 15 over 5. I guess I should write HA. It's 15 over 5. Excuse me. But that's just 3. And we're done. Now that's just 3. And so just to call out, well, what does it look like when your asymptote isn't 0 or none? Well, take a look right here. We've already seen that before. Here we saw an asymptote at -3. It's just a horizontal dashed line that my graph still hugs around in some way, shape, or form. So there we go. We've seen horizontal asymptotes. I'll see you in the next video.